For lesson 8.3, we're going to work with rational functions, which is very exciting. Rational, if you remember, means fractions. We get to work with fractional functions. The actual definition, a rational function is a ratio, which is another word for fraction, of polynomial functions. The domain, or the x values, are all real numbers, except any value that would make the denominator equal to 0. If I gave you a rational function of x plus 1 over x minus 3, this is my function. X can be all real numbers such that x cannot equal positive 3. If x were positive 3, 3 plus 1 would give me 4. 3 minus 3 would give me 0. And 4 over 0 does not exist. This is called a discontinuity. Okay, before we get into that more, let's talk about what a continuous graph is. Continuous graphs are what we've been doing thus far this semester. It's a graph that has no jumps, breaks, or holes. If you can draw the graph without picking up your pencil, then that's called continuous. Continuous graphs are lines. They can be parabolas. They can be absolute values. They can be circles. Anything that we have graphed so far. Discontinuous graphs, like the one in our first example, are a graph where there's some point that the x value is not real. This is called the point of discontinuity. This is that point where it makes the denominator equal to 0. In our first example, called a removable discontinuity, we have x plus 2 in the denominator. So I know that x cannot be equal to negative 2. If it were, then my graph would not exist. Here is a picture of the graph. And I can see here at negative 2, there's a point that I have removed from the graph. Thus, it's a removable discontinuity. It's an open circle indicating x cannot equal that value. A non-removable discontinuity. In this problem, I can see that x cannot equal 2. There's nothing that I can reduce here or remove. This is a picture of my graph. Right here at x equals 2 is called an asymptote. It's a line that my graph will never cross. Okay, so a removable discontinuity, it's a point on one point on a graph that I can take out. If you're looking at the equation, I can see that x plus 2 can be reduced or removed out of the equation. Non-removable, nothing can be reduced, and you have an asymptote in your graph. Okay, so our first problem, they want us to find the domain, all points of discontinuity, x and y intercepts, and then determine whether the discontinuity is removable or non-removable. Okay. In my first problem, to determine the domain, I'm going to look at the denominator. Remember, that's what my restriction is. That's what defines what x cannot be. I take my x plus 3, cannot be equal to 0, subtract the 3 across, so x cannot be negative 3. My domain is x is equal to all real numbers such that x cannot be equal to negative 3. My point of discontinuity is at negative 3. I'm going to abbreviate as POD, point of discontinuity, is at negative 3. The x and y intercept At my x-intercept, that's where y is equal to 0. So I'm going to plug 0 into my original equation. 0 equals x minus 4 times x plus 3 all over x plus 3. The binomials x plus 3 can cancel, leaving me with 0 equals x minus 4. Add 4 to both sides, and x is equal to 4. So my x-intercept, when y is equal to 0, let's write it as an ordered pair, is 4, 0. Y-intercept. That's when x is equal to 0. Plug it into my equation, and y equals 0 minus 4, 0 plus 3, and 0 plus 3. Well, the 0 plus 3's cancel, leaving me with y equals negative 4. My y-intercept is at 0, negative 4. And then the last part of the question asked if that point of discontinuity was removable or non-removable. If you look at the equation when you are solving for your intercepts, I can see that I canceled out the x plus 3's. Because I could cancel within my problem, that defines my point of discontinuity as removable. Okay, so let's look at one more of those. Letter B, find the domain, the point of discontinuity, x-intercept, y-intercept, and then determine if that discontinuity was removable or non-removable. Push pause as you do your work, and then resume play to check your answer. Here's the work that I had going through the problem. When I found the domain, I set denominator not equal to 0 because it can't equal 0, and I got that x was not equal to negative 1. So my domain is that x is equal to all real numbers such that x cannot equal negative 1. The point of discontinuity was at negative 1. There's nothing that I could cancel. Therefore, this is a non-removable point of discontinuity. As I solved for the x-intercept, I put 0 in for y. To get rid of my denominator, I could multiply by the entire binomial, which canceled them out. As long as I multiplied both sides by x plus 1, I'm okay. 0 times anything is 0. 0 does not equal 2. That doesn't make sense, which means there is no x-intercept. And for my y-intercept, I put 0 in for x, giving me 2 over 1. I write it as an ordered pair. My y-intercept was 0, 2. So that concludes the first portion of the notes, just going over domains and the different points of continuity.